Alyssa, check out my new project. I'm designing a new steel beam for a little shed in my backyard.
Hey Jal, that sounds cool, but isn't this the second time already? How are things going?
So I figured if I just pick a random size of steel beam, like I don't know, a 4 by 4 inch section, and hope for the best, it should hold up, right? It's a small shed anyway. Just a minute. Let me go ahead and then show it to you, my sketch. I'll just do the share screen. There you go. Do you see it?
It's still loading.
Oh,
There. Wait a minute, are you sure that's accurate? What's your basis for this? No offense, but this seems dangerously done.
oh, my cousin knows someone who does construction works, and this is what she said.
Hi, girl. You said you're gonna do a shed by yourself? You'll need my help again because the first one was a fail, right? I got you, girl. I have new connections. I heard from a friend of a friend of a friend in construction that steel frameworks are stress free. Once you know the perimeter of your structure, let your creativity run and connect them however you want. Each piece is already strong enough so you can expect that your shed will be strong and durable.
Alright, enough. Your cousin's friend of a friend of a friend did not even speak of calculations.
Oh, do I need to? I mean, it's just a small shed, no danger there.
Not quite. You need to calculate the load it will support first.
Oh, it can't be that heavy. Plus, I heard the steel is super strong. Isn't that enough?
It is true that steel is strong, but you can't just guess. You need to consider the factors like load type and distribution.
Low tech distribution? What do you mean?
There are dead loads and live loads that you should calculate to avoid overloading the beam and counter deflections.
That sounds complicated. Can I just roughly estimate? If it looks good, then it should do good, right?
It can be too risky to estimate by only looking. It's crucial to understand the principles behind it.
Okay. I'll start solving it properly, design and assemble the steel beams. But I'll be needing your help. I actually didn't remember any of this.
That's because you were busy doodling during the lecture. I believe that the professor said something like,
Alright, class. Remember, steel beams have several key properties crucial for their analysis and are fundamental for their design. For instance, we have the yielding moment, which is the maximum moment the beam can endure right before the yielding. And the section modulus is the ratio or the measure of strength resisting the bending stress. The plastic moment is the occurrence of the actual plastic deformation, displaying the maximum capacity of the beam and is of course greater than the yield. The elastic modulus, on the other hand, is the moment where the beam bends but goes back to its original form. The moment of inertia measures the distribution of the cross-sectional area about the neutral axis. We also have the deflection, which is the displacement of the beam under stress or load beyond its capacity. Bending stress is the internal stress because of the applied bending moments, while shear stress occurs when shear forces act upon the beam and usually happen near the supports. Now we have the buckling, which is the failure mode of the beam when subjected to compressive loads. This is why we have to conduct a thorough analysis with adherence to the building code to ensure the safety and stability of the structure. It also helps determine the shape and the number of steel beams that you can use for maximum efficiency and of course at the lowest possible cost. Ensure that the beams can safely support the loads while remaining within the acceptable limits of for the stress and deflection, because lives can be at great risk if these properties are not considered well.
Okay, I can recall the basics from there.
First, we have to gather information on the beams appropriate for their applications. Acquire all possible measurements in the areas of the flanges and the web. Calculate the load and select preliminary size for them. Compute the bending moment. shear forces, and section modulus before checking the deflection. Finally, choose the appropriate steel beam design that counters the problem and compiles with the code.
Wow, you are really listening. That's correct. But do you know how to actually solve it?
Well, I can solve it by drawing.
Alright, I will help you with the steel beam design. What do you have again?
The drawing that I presented a while ago, I'm actually using a W beam, A572 with grade 50, and then these are the dimensions. Let me show it to you again. I'll share the screen. There you go. Do you see it?
Okay. For the solving part, I'm gonna show you the solutions and formula.
Okay, sure.
I'm gonna share screen. Okay. So first, make sure to get the right measurement of the beam. Get the individual areas of the flanges in the web before adding them for later use. So here are the flanges and this is the web. This is the other flange. Then compute for the inertia by multiplying the base dimension to the cube height before dividing the acquired product by 12. Here. Next, measure the distance between the centroid area and the neutral axis for each component, which is here and here. You can now compute for the moment of inertia with respect to x-axis using this formula. Once you have the summation of each moment of inertia, divide it by the distance of the neutral axis to the top of the beam so you can get the elastic section modulus, which is this one. You can immediately have the yield moment when you multiply the elastic section modulus to the grade of your chosen beam, which is 50. After the face of the neutral axis, horizontally cut the beam like this and compute for each component's areas again to multiply it to the distance of each of their centroid area to the cut axis. Make sure you get the summation of their product before you divide it to the total area you got earlier in the first part of to get the position of the plastic neutral axis from the top. To solve for the plastic modulus, divide the new summation of the current computed areas in half. Separately multiply the distance of the plastic neutral area or the plastic neutral axis with 2 before multiplying it again to the half summation, and you'll basically have the plastic section modulus. Finally, simply multiply the grade 50 again to the plastic section modulus to complete the solution with the acquired plastic moment.
I see. So that's how it's solved. It's a long process, but they are easily done. I'm actually worried about the expenses if we'll have many beams to use. I guess I'll just leave them exposed.
Don't. That will cost you more in the long run. Exposed steel can rust over time. Consider protective coatings or paint them to prevent corrosion.
Wow, I didn't think about that. It's an excruciatingly long process to consider all these factors, but I guess proper design and practices are crucial for safety and efficiency. A well-designed steel beam not only supports the structure but also ensures longevity and reduces maintenance costs.
Looks like you're finally on the right track. You can do it on your own now since you understand everything, right?
Yup, thanks Eliza. I guess I've got a lot to learn about steel beams. I'll make sure to do it right this time.
Anytime. Remember, investing time in design now will save you a lot of trouble later.